Hello everyone, my name is Chuprov and thank you for this great opportunity to provide more details on my work, which is titled as Are Industrial Machine Learning Image Classifiers Robust to Withstand Adversarial Attacks on Videos? So this paper is titled by myself, by Shivam, by Raman, and by Professor Levin Reznik, who is a professor of computer science at RIT. Okay, let's go to the introduction. As you know, machine learning image classifiers are widely used in a variety of industrial applications. For example, this might be intelligent transportation systems, or this might be medical diagnosis and decision support making systems, and maybe some systems used for any kind of product inspection. These classifiers are trained on large data sets of images and videos to identify and classify objects with high accuracy, and usually these datasets are composed of the data of high quality. However, machine learning classifiers are also vulnerable to adversarial attacks. Adversarial attacks are carefully crafted inputs designed to fool machine learning models into making incorrect predictions. Adversarial attacks can be physical. For example, this might be a sticker put by an adversary on the traffic sign, or they might be digital. For example, it might be carefully manipulated images and videos by introducing some kind of noise or patterns into the image digital representation by the adversary. Adversarial attacks on industrial machine learning image classifiers pose a serious threat to the safety and reliability of these systems. For example, an adversary could craft an adversarial video that causes a self-driving car to misidentify or misclassify a traffic sign. Or, for example, this might be an adversarial attack against a medical imaging system to misdiagnose a patient. In this work, we investigate the robustness of industrial machine learning image classifiers to adversarial attacks on videos. Specifically, we focus on the intelligent transportation system use case, in which machine learning classifiers are used to detect and classify objects in videos captured by vehicle dashcams. In our work, we used Amazon Recognition, which is a commercial industrial machine learning service to classify objects in videos from the BDD 110K dataset, which contains recordings captured by vehicles' dashcams driving in various lightning and traffic conditions, for example, on the busy city streets or on the highway. First, we selected 25 high-quality videos with clearly visible patterns of interest. In our case, we concentrated on two labels: traffic lights and road signs, which are standard labels provided by the recognition. As performance metrics, we employ the confidence score, also provided by recognition, and the rate of correct decisions, which we calculate manually based on the results obtained. We applied simple pixel manipulation adversarial attacks to the videos by randomly changing the color to of some pixels to white. This is the kind of noise introduction into the videos. We varied the intensity of the attack by changing the percentage of pixels that were affected by this noise. We evaluate and record the performance demonstrated by Amazon Recognition for each of the attacks intensity investigated. Here on this slide, you can see some examples of the videos which were attacked by our pixel manipulation, or in other words, by adding noise. As you can see, when the intensity grows, the percentage of the affected pixels also grows. So yeah, and as you can see, some patterns might be unrecognizable, but for a human eye, we can tolerate this intensity, even up to 15%. But for the machine learning system, as you will see later, this might be a large problem. In our work, we found that recognition's confidence scores for both traffic lights and road signs labels decreased as we increased the percentage of affected pixels. At a noise level of 5%, recognition's confidence score for traffic lights labels dropped from 99% to 90%. For the road signs labels, the confidence score dropped from 95 to 80%. These results indicate that recognition is vulnerable to even simple and low-intensive pixel manipulation adversarial attacks. We also found that recognition performed better on the traffic lights category than on the road sign category, with higher confidence scores and correct decision rates across all noise levels. This is likely because the traffic lights are typically larger and have more distinct features than the road signs. Finally, we found that the average file size of the adversarial videos grew as we increased the noise level in our videos, but this growth slowed down after 5% noise level. This is because the amount of additional information needed to encode the adversarial noise decreases as the noise level increases. So in these figures, you can see our results. The confidence score for the maximum, the average, and minimum results demonstrated by the Amazon over the all video set of 25 videos. And here on the right side of the figure 2, you can see the correct decisions, the rate of correct decisions made by Amazon. On the left side, you can see examples of the videos attacked by various attack intensity. So you also have seen the videos, and this is just the examples of the frames from another video. Okay, to conclude our work, Amazon recognition is easily fooled by small changes to videos, such as randomly changing the color of some pixels to white, as we demonstrated in our work. This means that an attacker could create a video that would cause recognition to make a mistake, such as misidentifying a traffic light or a road sign. Recognition is better at detecting traffic lights than road signs, and its performance on both tasks decreases as the amount of noise in the video increases. This means that attackers may be able to target recognition with more sophisticated attacks that are tailored to specific labels or videos. Our research shows that commercial machine learning systems are not as robust as they should be, and that they are vulnerable to even simple and low-intensity adversarial attacks. This is a serious concern for industrial applications that rely on machine learning systems to make important decisions. As our recommendations, we need to develop more robust machine learning solutions for industrial applications. One way to do this is to retrain machine learning models and data that contains a variety of adversarial attacks. Other measures, for example, such as using ensemble methods to combine the predictions of multiple classifiers and deploying anomaly detection systems, can also be used to mitigate the risk of adversarial attacks. Thank you very much for listening to my presentation. If you have any questions, please let me know by my email, or you can approach me during the workshop if you are attending in person, and I will be happy to talk with you. Thank you very much and have a wonderful day.